We're going to look at how to approximate values using a Taylor polynomial. Now, in my previous video regarding Taylor polynomials, I talked about what a Taylor polynomial is, how to expand it, how to form it and write it. This part is showing you that you could also write it as a series. So in the condensed form, a Taylor polynomial becomes a Taylor series where we have the nth derivative, depending on which n you're on, evaluated at the center c, divided by n factorial times x minus the center c raised to the nth power. So in expanded form, you would count through, let's say I wanted like a 5th degree Taylor polynomial, I would go from n equals 0 to n equals 5 and actually write out each of the different terms and have a summation there. Maclaurin series is the same thing as a Taylor series, the only difference being it is centered at x equals 0 or c is equal to 0. So it's still the same formula, but instead of having a constant number c for your center, you're going to have 0 plugged in. Now these are very useful in approximating trigonometric, logarithmic, exponential, etc. values, especially in the days before you had calculators. So like 200 years ago, you couldn't just pull out your calculator and type in natural log of 1.1. You had to actually use a Taylor series or Taylor polynomial to approximate the value to the best ability that you could. And of course, the higher degree you go with the Taylor or Maclaurin polynomial, the more accurate the approximation actually is going to be. If you only do a 1st degree Taylor polynomial, it's not going to be extremely accurate. It'll be close, but it won't be extremely accurate. Versus doing something like the 7th degree Taylor polynomial. That will be a lot more accurate. They also use this today in computer programming. So when you do actually type in natural log of 1.1 on your calculator, the calculator is actually using an algorithm with Taylor and Maclaurin polynomials and series to approximate the value and give you the answer of, let's say, natural log of 1.1 or whatever it is you're typing in. So I want to begin by finding the Taylor polynomial p sub 4 for f of x is equal to ln x centered at c is equal to 1. So what this means is I need a 4th degree Taylor polynomial for ln x centered at x equals 1. So like we did in my previous video, you're going to have to actually generate out all the different derivatives all the way down to the 4th derivative. So let me just start by saying, okay, well, f is ln x, f prime is 1 over x. I'm going to go ahead and rewrite that as x to negative 1 to make it easier on the next step. F double prime is negative x to negative 2. F triple prime is 2x to negative 3. And the 4th derivative would be negative 6x to the negative 4th. Now, because my Taylor polynomial needs to be centered at c is equal to 1, now I need to evaluate all the different derivatives and functions at x equals 1. So on the side, I have f of 1 is equal to ln of 1, which is 0. F prime of 1 is 1 over 1, which is 1. F double prime of 1 is negative 1 over 1 squared, which is negative 1. F triple prime of 1 is going to be 2 over 1 cubed, which is 1, so 2 overall. And then my 4th derivative, evaluated at 1, would give me negative 6 over 1, which is negative 6. Now that I have my coefficients that I'm going to get from the derivatives, I can form my Taylor polynomial. So then p sub 4 of x would equal, the first term comes from f of 1, so that's going to be 0. And then I have plus f prime of 1 times x minus 1. So f prime of 1 is 1 times x minus the center c is 1. Plus now I need the f double prime of 1, which is negative 1, so I'm actually going to change that to minus. And then it's negative 1 over 2 factorial times x minus 1 squared. Then I take the 3rd derivative coefficient, divide by 3 factorial, times x minus 1 cubed, and then minus the 4th derivative value, divided by 4 factorial, times x minus 1 to the 4th. This is my fourth degree Taylor polynomial of ln x centered at x equals 1. Now what I want to do is take that and use that to approximate a value. Okay, so here I've copied the fourth degree Taylor polynomial, p sub 4 of x, and I want to use that to find p sub 4 of 1.1. Well, all I would need to do is replace every x with 1.1. So p sub 4 of 1.1 is going to equal 1.1 minus 1 minus 1 over 2 factorial times 1.1 minus 1 squared plus 2 over 3 factorial times 1.1 minus 1 cubed minus 6 over 4 factorial times 1.1 minus 1 to the fourth. And so if I simplify all that, I end up with approximately 0.095383, etc. So what I want to do is, this is an approximation of natural log evaluated at 1.1. It's not accurate because I formed a Taylor polynomial to approximate it, but what I really want to do is compare, well, how would that actually compare to the original natural log of 1.1? So if I want to find f of 1.1, that's just taking natural log, plugging in 1.1, and this is where you would use your calculator. So natural log of 1.1 is approximately 0.095332. Notice they're very, very close together. So the concept from this that we gain is, well, how close are they together? What is the actual error in approximating it with a Taylor polynomial versus looking at the actual amount? So if I want to look at the error of the approximation, I need to subtract the two. So the error is found by taking the absolute value of your f of 1.1, which is the original actual amount, minus the approximation, which is p sub 4 of 1.1. So if I take the natural log of 1.1, which was 0.095332, subtract off the approximation found by using the Taylor polynomial, 0.095333, then I find that my approximation ends up coming out to 0.0000019. That is a very good approximation, especially given the fact that I only made it a fourth degree Taylor polynomial. If I went to, let's say, the fifth degree Taylor polynomial or the sixth degree Taylor polynomial, it would have even a smaller amount of error. But for what it is right now, that's a tiny error, so this is a very good approximation to the actual amount of natural log of 1.1. So you can see why they would use a Taylor or Maclaurin polynomial or series to actually approximate values back in the day when we didn't have a calculator or computer readily available. Now, graphically, I want to show you what this means as well. So here, the red curve represents natural log of x. So that was my original f of x. And the blue curve represents p sub 4 of x. So that's my Taylor polynomial of fourth degree centered at x equals 1. So notice, right along this area right here, from about this point to this point, the curves are basically indistinguishable. They're about the same. And so anywhere in that area, the Taylor polynomial is such a good approximation that it's hardly any different from the actual value of natural log of x. However, that changes if I wanted to use the Taylor polynomial to approximate the value at 3. So f of 3 would be ln of 3, which is up here. P sub 4 of 3 is way down here. Definitely not a good approximation at that point in time. They're not even the same sign value anymore. ln x of at x equals 3 would be positive, but the Taylor polynomial would give you a negative number. So in that case, what you would need to do is change your center. So before, when we had everything centered at x equals 1 and we plugged in 1 to all the derivatives, now you would just want it centered at 3 and plug in 3 instead of the 1. So you can change where your center is to make sure that they align closer together and it's a better approximation. Of course, the approximation is only going to be valid and really good around the area that you're centered at. So in this case, x equals 1 was the best place to center it, because if I'm trying to find f of 1.1, 1.1 is right here, And notice those curves are so close together that it's a very, very good approximation, which is why we ended up with a really tiny error at the end. And so they're basically the same amount in terms of the value, so it would be a good approximation for that. So hopefully that helps you out with understanding how to approximate values using a Taylor polynomial. Of course, you could do the same thing with a Maclaurin polynomial, the only difference being with Maclaurin, you're centered at x equals 0.